SwayamPrabha. Digital India. Educated India.
Welcome back. So we are in the middle of the discussion of this G equation or level set based approach, where we have already looked at the G equation for the corrugated flame lead regime, and also we have seen how G equation actually differs when you go to thin reaction zone regime. Now we would like to see how you can combine these two and come up with one equation which will be applicable to both the regime. So we will normalize the G equation, normalize G equation with Kolmogorov scale, like eta time scale u eta. Our T star would be T by tau eta, Xi star would be Xi by eta, Ui star would be Ui by U eta, and kappa star would be eta kappa. Del del Xi star is eta del del Xi, and delta star is eta delta. So now if I use this normalization parameters, which we can write the G equation like del G by del T star plus Ui star delta star G SLS by U eta delta star G minus d by nu kappa star delta star G magnitude. So this is what we can write. We will look at now some order of magnitude of this term. So this is the equation we are now dealing with. This is kappa star delta star G. Now we have this term, we can look at this term. So this is order of Karlovich number to the power minus half, and this guy is order of 1. So if we non-dimensional thing, the derivatives and Ui kappa star, which will be order of 1. So we can see this non-dimensional form of these things. Now if you look at typical flame, what will happen, that Sc equals to nu by d, which is 1, that means d by nu would be order of 1, and SL by U eta, when Karlovich number is U eta square by SL square, so SL by U eta is Karlovich to the power minus 1, and SLS will be order of SL. Now one can see when you have thin reaction zones where your Karlovich number is greater than 1. So your curvature term is dominant. Why? Because if we look at that equation again, del J by del T plus ui star del star G equals to SLS by u eta del star G minus d by u kappa star del star G. So, this is order of kappa to the power minus half, this is order of 1. So, when you go to thin reaction zone, if kappa is too high, so it is the curvature which will dominate. Now, at the same time, if you go to corrugated flamelet zone, flamelet regime, where Karlovich number is very small, this term is going to dominate. So, SL term is dominant. So, if you take the leading order equation in both regime, so you can write rho del Z by del T plus rho ui del xi equals to rho SL naught delta G minus rho d kappa delta G. So, this term with the assumption that rho u equals to rho u SL0, which is constant, and this is also constant. So, now we can use our knowledge of statistical description and we can actually define this. Now, we can see the probability density function of finding G, which is G naught equals to 0. So, if you consider a steady one dimensional premixed flame at position xf, where xf is minus infinity to infinity xfx dx. Now, you can define the flame brush thickness, which is LF. So, the LF square would be x minus square minus infinity square fx dx. If G is distance function, what we get G prime is minus x minus xf. Now, this is the flame front and this is the instantaneous flame front, and then this is the mean. This is instantaneous, this is mean. So, this one can think about G double prime, and if you see this is what is going to happen. So, this is our average T profile and this is instantaneous T profile. Okay. So, we can write for the Fabry-Min equation, which is rho bar plus rho bar xi plus rho xi rho bar SL0 sigma bar rho d kappa sigma this, and along with that we get or write another equation which is in terms of variance. So the variance equation is rho bar square by del t rho bar ui square del xi plus xi rho bar ui prime equals to minus 2 rho bar ui prime g prime del xi rho bar omega kappa rho d kappa sigma, where sigma equals to mod of del g. So this is then can be interpreted as an area ratio of the flame front AT by A, and variance actually describe the average size of the flame. Now in the variance equation there are terms like sink terms. So the terms which is the kinematic restoration, it is the this which is rho SL naught G double point sigma by rho bar. Scalar dissipation term which is del xi double prime by del xi which is square by rho bar, and these are two which are modeled as omega plus this is Cs epsilon by k g prime square by this. So this is how one gets some closer approximation for that. Now we invoke the information of the turbulent burning velocity. So then we can write rho bar ST0 del G equals to rho SL0 sigma bar, where we can say STA equal to SL AT. Now the Fabre mean equation will get rho bar, or rather it's modified now, equals to rho bar ST0 delta G minus rho diffusivity kappa del G, and the variance which is rho bar plus rho bar ui del xi dot rho bar plus 2 rho bar dt minus Cs rho bar by k bar. So this is what we get, two equations in that form. So now we have used the turbulent burning velocity expression using the Damkohler theory, and you can see how ST by SL actually varies, and that's we want to bring in. This is the mean, this is the G prime. So the Fabre mean G bar is G naught plus x minus xf. So the Fabre PDF would be 1 by root over of 2 pi G prime square at naught minus G by G bar square by 2 at naught. So now we can find out the mean temperature or any other scalar like this, minus infinity to T of G PDF of G dg. So this guy is the T of x from the laminar premixed flame without strain. So we can use this and correlate these things. Now this is how one can use this G equation thing, and now when you go to LES for this premixed combustion diagram, that gets slightly modified, where this delta is your grid size or filter size, and you can use a different these things. So that brings to the other part of these things, which is thickened flame or progress variable kind of situation. Progress variable we have looked at it. Now we look at the thickened flame based approach, which is also very much applicable to. Now one important point to note here is that this thickened flame kind of approach is only applicable in the premixed flame front. So this is not very much applicable in the RANS application, this thickened flame kind of approach. Now what happens here, as we have said that laminar flame thickness, which is or premixed flame thickness is quite smaller, and sometimes it may possible that the flame front actually lies within the grid cell, which is order of this. So that means one small computational grid is quite larger than this flame thickness. So then the question is that how do we capture this flame front? So the idea behind is that you have a very thin flame front which cannot be resolved on the computational grid. So what is idea is that if we actually artificially, that's why it's called also artificially thickened flame model, ATF. So the whole idea is that if we actually artificially modify the flame front, that means for example this is our grid and this is our flame thickness. Now what we want to do that you modify that thing and the flame front is thick. So once that happens, then we can resolve that flame front thickness in the grid. So the whole idea is that if we artificially thicken the flame front, then we would be able to resolve in the computational grid. Now the point comes how one can artificially thicken the flame front. So the whole idea behind that thing is that the way this thickening is done, that it doesn't change the basic flame properties like laminar flame speed and flame thickness. So the flame thickness is typically is a ratio of diffusivity and a ratio of the flame speed, and flame speed is the diffusivity in the reaction rate. So the way thickening is done, so if you look at this, if you artificially only thicken the flame front by a factor f, then the speed will be reduced by that factor. So to avoid that thing, the thickening is done in such a way that you increase this diffusivity by a factor f at the same time. So essentially this would like SL naught, which will look like f into dth into b by f. That means at the same time you reduce the reaction rate by same factor, that the way it is done, it doesn't change those properties. So by doing that, so which means the unthickened flame front or thickened flame front is not going to behave in a similar fashion that like the actual flame front used to behave. So, now once the flame front is thickened, this is not going to behave like to the actual flame front. So, the turbulent flame speed need to be invariant under the scaling transformation. Now, if we look at the Damn-Coulomb number, which is a ratio of flow and the scale, so this also gets reduced by a factor. So, the solution to that, because that means we are by artificially changing the flame front, also we are changing the some of these properties, we are changing the Damn-Coulomb number of the flame front. So, it may belong to a completely different zone. So, the way this is done, that we multiply the thermal diffusivity and resolve reaction rate by efficiency factor E in order to have the correction in or the correct turbulent flame speed. So, this E is obtained from the DNA study. So, now the equation would be like that. This is our diffusion and the reaction term on the right hand side, which is modified now with a factor E, then thickening by F, and the reaction term is multiplied with E by F, and this E, this flame linking factor or whatever is that efficiency function, which is a strong function of all these parameters like U prime, SL, delta F, delta L. So, now by doing that, what we do that you change. Now, there are some advantages, some disadvantages with this particular model. It solves for individual YI, that means it. So, this particular model actually solves for individual mass transfer equation, and individual mass transfer equation, this diffusivity we can actually, and this term actually one can think about this ED as an like diffusivity plus E minus 1D. This is our this particular term, this correction factor, one can assume that this is your component of the molecular diffusivity and this is the component due to turbulent flux. So, that is why it is consistent with other governing equations, but the advantage is that it solves for individual species mass transfer equation. So, one can now use some sort of an detailed kinetics, but in reality it is not too much of detailed kinetics has been used in this kind of modeling framework, because that becomes computationally expensive. Secondly, because of this thickening and all these things, the minor species cannot be captured very nicely. So, this is one of the drawback, and there are of late there are lot of these different modification to these wrinkling factors are proposed, and also one can use or look at the dynamical or dynamic variant of this thickened flame approach or dynamically modified this thickened flame approach. So, these are the some of the latest situation of this particular modeling, and one can look at the literature to find the latest situation. Now, moving to the progress variable kind of approach, where we can use a different notation like this instead of C. So, there also we will use two transport equation for this particular progress variable, one transport equation for the mean progress variable like unsteady convection, diffusion and source term, and this is modeled as rho SD, and once we use the filtered equation, then we get this, and there would be, which is also modeled as right hand side is SD del theta. So, there are terms which are unclosed and one has to do that. Now, closure for this displacement term. So, the subgrid scale can be viewed an ensemble of fronts of propagating with laminar flame speed of an unstaged flame. So, the amount of the flame fronts characterized by the flame surface density is that rho SD del theta would be equivalent to rho U, SL and surface density. Now, we can model for the surface density, which is this factor into delta theta. This is called subgrid scale wrinkling factor, where subgrid scale flame front density by the density in the resolved field. So, this is now one can use this filter or averaged burning velocity, which either in DNA situation you get this, this is an instantaneous flame front, this is the mean flame front, where this is your turbulent burning velocity, that is displacement speed, and this is the subgrid stress. Now RANS, the speed propagation is relative to the mean, and LES, this is to the resolved reactance, and one can correlate from this and use those expression. And we have already seen there are different kind of correlations which are available, and for more of this you can, so the relationship between this is that in RANS, ST usually expressed via correlation in the RANS constant, and when you look at the grid convergence test, so in the grid convergence tends to 0, this would be the grid independent, that is, but in LES, ST delta part of the subgrid still. So consistency check is that when delta tends to 0, it should goes to DNS. So that is where it is important. So that means they are consistent in nature, so that you can use this. So a good model for ST delta would allow to compute the ST, and RANS model based on flame surface density can be used to predict also ST. So the one thing is that there are different kind of closures which are available to model one or the other flame, I mean the flame speed, burning velocity and all these things. And as we have seen more details of these burning velocities, one can find out this review paper in Progress in Energy and Combustion Science, which typically publishes the review paper on that particular field, where you can see there a comparison or collection of different correlations there, all the advantage, disadvantage and all these things. So one of the correlations which is in universal form can be used is that ST by SL is constant B1 B2 into U prime by SL to the power B3, and then this Lewis number to the power B5. Now because accelerating flames create compression waves and sometimes a shock ahead of it, the flame finds itself in reactants that are at elevated pressure and temperature. Change in the values of SL be taken into account. So this is the whole idea that one has to take into account. Now slightly more advanced remark, which is that importance of the molecular transport, which says that the influence of molecular transport on turbulent flame speed appeared to be one of the two major challenges to premixed flame turbulent combustion community. So again these things are detailedly discussed in this review paper by Progress in Energy and Combustion Science in 2005, and thermodiffusive effects are observed even when the turbulent intensity and Karlovich numbers are large. This is in another paper by Driscoll in 2008. So where it shows that this ratio with the U prime by SL and for difference equivalence ratio that becomes unstable. So these are the advanced remarks and advanced topics or advanced issues which one can find in this particular review kind of journal, where you can see lot of review paper which come across. So that pretty much closed down the discussion on our premixed flame. Now we will stop here today and continue the discussion on non-premixed flame in the next lecture.